Okay, we have derived these formulas. You don't need to you don't need to worry too much about the derivation of these formulas, but you do need to understand which formula is for what purpose. For example, we want to evaluate a project, and usually we know the future, or at least we have an estimate of the future cash inflow and outflow of the benefits and costs. And in such cases, we want to discount all future dollars back to present times. So we need to use Formula 4. Formula 4 is the main formula we want to use for our purpose. Formula 6 is the present value of an ordinary annuities. So to understand this formula, say we have a $R ordinary annuity for N years. The present value of this annuity is just the $R times a factor. And this, we actually have a name for this. This is called annuity factor. Annuity factor. Intuitively, this annuity factor should depend on two things. First thing is discount rate. The more we discount it, the heavier we discount it, the smaller the annuity factor is going to be. Second thing is the number of payment periods. Not surprisingly, the higher number of payment periods, the higher the annuity factor is going to be. Okay, if these are dollars payment cash flow per period that occurs forever, then we end up in having this perpetuity, and that's the present value of the perpetuity. If this perpetuity is growing at a growth rate, if this perpetuity is growing at a rate smaller than the discount rate, then we can calculate this growing perpetuity present value as this. So it's just R divided by discount rate, take away the growth rate. In contrast, if the growth rate is higher than the discount rate, then we end up in having an infinite number for the present values, or the present value actually explode. So that's Formula 8. Formula 9 is to convert the annual effective rate when the interest rate and the compounding periods are not the same. And Formula 10 is the what we call Fisher equations, converting the real discount rate, real interest rate, and nominal interest rate by accounting for the inflation rate. So when we deal with the practical issues, we must know kind of these formulas in order to compute the NPV associated for a project. And here we're going to assume that the discount rate, the social discount rate, is given. So we know that. Okay, we are going to go through in this topic. We are going to go through a number of issues here. Right, so NPV is equal to present value of benefits, take away present value of costs. So we can write for present value of benefit is, so this, let me put a timeline here. So there's a benefit B1, B2, B3, and Bn, so on and so forth. And each, we can discount each Bi back to present time, which is Bi divided by 1 plus I raised to the power of negative I. Okay, so the present value of benefit is this. Similarly, if we also have cost here, C1, C0, C1, C2, C3, so on and so forth, Cn, then the present value of this cost can be calculated as this. And the NPV is just the difference of this present value of benefits and the present value of costs. Alternatively, we can calculate net benefit for each period and then discount it back. Okay, first example. A government agency has to choose between two alternative projects. So we are comparing two projects now. Project A yields a benefit of $10,500 4 years from now. Project B yields $5,500 4 years from now, and an additional $5,400 5 years from now. And discount rate we know is 8%. Okay, let's put these cash flows into the timeline like here. Okay, one thing you want to be aware is that, so we have a timeline like this, 0, 1, 2, 3 until n. So the tick here, the tick 0 here clearly represent present time. What about tick 1, tick 2? So does tick 1 represent the beginning of year 1, the end of year 1, or the middle of year 1, or other time points in the first year? Okay, you want to be aware that this tick here represents end of year 1. So all tick here on our timeline represents end of the year. How to understand this? Let's think that I'm standing at 0. So that's present times. If I move one step forward, I start getting if I move one step forward, I get into the beginning of year 1. Okay, so this 0 here represents present time, but also the beginning of year 1. Then I keep going until I reach 1, tick 1. Then that's end of year 1. Okay, so this tick 1 here represents the end of year 1. Then I move one more step forward, I get into the beginning of year 2. So now you want to realize that this tick 1 also represents the beginning of year 2. Tick 1 is end of year 1 and the beginning of year 2, and so on and so forth. Okay. Right, okay, so we record the cash flow. Project 1 is $10,500, and it occurs in year 4, end of year 4. Discounted back, so discount back, we get it 10 times 1 plus 8%, which is discount rate, raised to the power negative 4, and that's $7,718. Similarly, for project 2, there's a cash flow of $5,500 in year 4, and there's another one in year 5, which is 5,400. And discounting back, for the second terms, for the first terms, raised to the power -4. Then we get the present value of these two terms, sum them up, and we find that it's actually the same as the project 1. So you're going to conclude that these two projects yields exactly the same present value of net social benefit, and they are the same. Okay, let's move to second examples. A district library is considering purchasing a new information systems that will give users access to a number of online databases for 5 years. Okay, this is the project you want to assess. Benefits are estimated to be $100,000 per annum. The system costs $325,000 to purchase and set up initially, and it also requires $20,000 to operate and maintain each year. So that's the information we gather. Okay, we want to compute the present value of the NPV of this project. So after 5 years, the system can be sold for $20,000. So this is scrap value of the system. Discount rate is 7%. Okay, let's put all the cash flows into the timeline like this. So 0, 1, 2, 3, 4, 5. Right. Benefit $100,000 each year for 1, 2, 3, 4, 5 years. So the project lasts for 5 years, and at the end of the 5th year, you can sell the system for $20,000. So that's the scrap values. On the cost side, initially there's purchase price and setup costs. That's $325,000, and then there's a maintenance costs. Maintenance cost of $20,000 for 5 years. Okay. Now we have set up these timelines. So let's discount it one by one. We can do it one by one. So the first terms here, $100,000 in year 1 benefit. So the present value of this is 100,000 times 1 plus 7%. That's the discount rate raised to the power -1. We get these numbers: 93,458. Similarly, for the second terms, third terms, fourth terms, fifth terms. So fifth terms, the present value of this, the present value of $85,558 is the present value of this. Similarly, we can do it for the cost. The first item of cost occurs at time 0, so it's already present values. So we don't need to discount it. For the next five $20,000, discount them back term by terms, we get present value of the present value. Add them up, we get a present value cost. Similarly, we get a present value of benefit. So present value benefit, take away present value cost, we get an NPV. So which is $17,276, and the NPV is positive. We conclude that this project is efficient, we should go ahead with it. Okay, so that's the second examples. Look at this timeline. Rather than discounting the item, discounting the benefit and cost item by items, we can actually observe some sort of nice feature of it. First one is this cash flow. It's actually is an annuity of 5 years, so we can actually apply the annuity formulas to compute the present value of this annuity. Similarly, for this $20,000 costs of 5 years, again is an annuity, so we can apply the annuity formula to get the present values, and you should get exactly the same NPVs. Okay. Right. Let me give you a task here. Okay. In these examples, all the benefits, all the items of benefits and cost occurs at the end of the years. Okay. What about if, say, these benefits occurs in the middle of each year, and you compute present value of this project? That's a task for you. Right, and here is the timeline where we compute the net benefit for each year. So net benefit for each year, and then discount it back, get the NPVs, and we see that the NPV is exactly the same. So here is different ways of computing the NPV. So you want to be careful about the timing of the benefits and costs. Different timing, you will end up in having different NPVs. Here timelines are very useful ways to specify exactly when benefits and costs occurs, and make sure you are clear that each ticks represent the end of the years, so that you record the timing correctly. Okay, so that's the task. Okay, or that's actually second task now. So benefits occurs at the beginning of each year. Everything else unchanged. So what is the associated NPV? So beginning of the year, we can see that this occurs beginning of the year. So first terms is already beginning of year 1, which is year 0, okay, which is present values. So you don't need to discount, okay. And the NPV in the end, we can find higher NPVs than occurs at the end of years. And for the task that are left to you, when the benefits occurs in the middle of years, it should also find a higher NPV compared with the case when the benefits occurs at the end of the years. Right. Okay. Sometimes when we are comparing two projects, sometimes it can be the case that these two projects, they do not have the same time frame. It could be one project lasts for 30 years. The second project lasts for only 10 years. So in such cases, how can we compare them? Right. So we have two ways of comparing them, actually. Okay, let's look at examples first. A government-owned electric utility company is considering two alternative proposals for new sources of energy. So one is hydroelectric dams, which will last for 75 years. The other is a cogeneration project, CGP, that will only last 15 years. So now we are comparing, you want to be aware that we are comparing a project of 75 years with another project of 15 years. So we need to make sure, we need to account for this, because otherwise we will be comparing apple with bananas. Okay. The discount rate is 8%, and further suppose that we already calculate the NPV for the hydroelectric dam projects to be $30 million, and the NPV for the cogeneration project to be $24 million. Can we just, based on these two NPV, can we just conclude that, okay, hydroelectric dam project is better than the cogeneration projects? The answer is no, because we haven't, for these two NPVs, they do not consider the fact that these two projects have different lengths of periods. Okay. If we compare 30 with 24 directly, then we are comparing apple with bananas. Okay, two appropriate methods to evaluate projects with different lifespans. First one we call it rolling over the shorter projects. Second one is equivalent. We call it equivalent annual net benefits methods. Okay, what do we mean? Okay, rolling over the shorter periods, the shorter projects. The idea here is that, okay, the hydroelectric dam projects last for 75 years. The cogeneration project lasts for 15 years. So within the 75 years, we can actually roll out 5 cogeneration projects, right? So the idea here is that, okay, let's roll over the shorter projects so that it has the same number of periods as the longer projects, and then compare the NPVs of the long project and the NPV of the rolled over projects. Okay, and such that we can be sure that we are indeed comparing apple with apples. Okay. So if project A spans in times the number of years as project B, then assume that project B is repeated in times and compare the NPV of these n repeated projects to the NPV of one project A. All right, so we can have a okay, so the hydroelectric dam project has an NPV of $30 million. Okay, for the cogeneration project is $24 million. But it only lasts for 15 years. So let's roll over this cogeneration project 5 times to get the same number of periods. So 5 times we got this. We got 1, the first one, the first cogeneration project, which has an NPV of 24 million. The second cogeneration project, which has NPV, but now it should be you should be aware that this NPV is NPV in year, 15. Okay, because that's the second cogeneration project, so it's 24 million. For the third cogeneration project, the NPV is also 24 million, but it's in year 30. So fourth, similarly, is 24 million in year 45. Fifth is 24 million, but it's in year 60. So now the first cogeneration project is present value in year 0. For all the other terms, is we need to discount them back, right? So the second cogeneration project is $24 million. That's year 15. So discount it back, we get present value in year 0. For the second one, third one, fourth one, we get $34.94 million. Okay, so now we compare this $34.94 million with the $30 million NPV of the hydroelectric dam project. And here we're going to say that the cogeneration project is actually better than the hydroelectric dam projects because it has a high NPV. Right, that's the first method. Second method is called equivalent annual net benefits method. Okay, the idea here is that, okay, what about this hydroelectric dam project lasts 75 years. Okay, this compute an equivalent annuity that's associated with this compute an annuity that's equivalent with this hydroelectric dam project. So essentially what we want to find out, if we get a cash inflow of how much $R, suppose, for 75 years, then present value of this $R for 75 years is equal to the NPV of this hydroelectric dam project. And this $R, we call this associate, is the equivalent annual net benefit of this hydroelectric dam project. We can do this calculation. Remember, let me remind you of the formula for annuity, so which is per period payment times an annuity factor, which is depends on interest rate, discount rate, and the number of periods. So 1 minus 1 plus I raised to the power negative n divided by I. So that's the annuity factor. Okay, so we can calculate this for the hydroelectric dam project. In addition, we can also calculate this R for the cogeneration project. And let's compare these two R, right? So these two R, the comparison of these two R is fair, okay? Because this R is the per period payment, is the annual payment, okay? So we are indeed comparing apple with apple, not apple with banana. All right, so this is the idea of equivalent annual net benefits methods. The EAMB is the amount received each year for the life of the project that has the same NPV as the project itself. So essentially, we are converting this project into an annuity, okay, and compare the annuity payment of each period. The EAMB of a project is computed by dividing the NPV by the appropriate annuity factor. So this ARN is annuity factor here. So we need to calculate the annuity factor first, and then get the EAMB. Get R. This EAMB is R here. Okay. The appropriate annuity factor is the present value of an annuity of $1 for the life of the project in years. And when we calculate these two R's, obviously, one would choose the project with the highest EAMB, highest R. So let's compute EAMB. So for the hydroelectric dam project, the annuity factor is 1 minus 1 plus I. We know that the interest rate is 7%. And the number of periods is 75. And that's equal to 12.461. So the associate annuity is $2.407 million. 30, that's the present value, divided by annuity factors, we get the per period payments according to that formula. Similarly, the annuity factor for the cogeneration project is 1 minus 1 plus 7% raised to the power of negative 15 divided by 7%, which is equal to 8.559. So the associate annuity payment is $2.804 million. And we compare these two figures, and we conclude that a cogeneration project is better than the hydroelectric dam projects. All right, this is the second method of comparing projects of different lifespan. All right, so essentially the essence here is that we want to make sure that our comparison is fair. It's apple to apple, not apple to banana. However, our computation here is not perfect actually. There's something that is not accounted for in our calculations here. No matter we use the shorter rolling over shorter projects or equivalent annual net benefit methods. All right. This point is not accounted for in the computations. Shorter projects also have additional benefits not included in the computation, because one does not necessarily have to roll over the shorter projects when it is finished. A better option might be available at the time. So suppose say, okay, I'm going to implement the cogeneration project, which lasts for 15 years. So at the end of 15 years, wow, there may be better technology, there may be more efficient technology available then. Then at the time, I have an option to use these better technologies. And this is not accounted for in our comparisons here. Okay, so that's what we want to cover here for this topic.